Hello and welcome to my talk about OpenMP Interop, which can be used to combine math library calls of GPU vendors with OpenMP. I'm Tobias Berners and I work for Libre. Quickly about me, I'm contributing to the OpenMP specification, but I also contribute to a compiler, to GCC compiler in the area of GPU offloading and OpenMP. And in my academic past, I was doing some number crunching related to physics, so I know the user side as well. I work for Libre, who gets paid for a service company for work on compilers, Linux kernel, Android, and the like. But let's start. A typical program is an MPI program with thread parallelization, usually by OpenMP. And at some point, one wants to use GPU libraries, and GPU vendors ship with them supporting fast Fourier transformation, linear algebra, sparse or not, LAPACK, solvers, and random number generation and the like. And the following kind of applies to both programs which don't really have offloading, but also those that do, where then one has heavy calculation using code on the host and on device concurrently, and then of course synchronization and dependency plays a role. So let's start. And OpenMP features and especially Interop now help with ensuring the library and OpenMP works actually on the same device, handling the dependencies, and also makes it possible to abstract things. So at the call side, one doesn't have the heavy part of the runtime library specifics, but one can put them at some separate parts. So let's start with an example. As example, I've chosen blast routine, which does a scalar times vector plus vector calculation and stores the result into one of those vectors. I use cuBLAS, well, some vendor library I have to use, and CUDA is most popular. And well, the actual call is highlighted here in line 8. That's the cuBLAS DAXP call. But of course, much more is needed. On one hand, one has the memory and data handling, so one needs to initialize variables, partially somewhere outside, but in many cases also immediately before use. And one makes to make sure that the memory is available on the device, because in many cases the functions require that's device accessible, the pointer, or directly hosted the device. And there's also some overhead because one needs to create a streaming object and associate it with CUDA BLAS. In the first step, I look at the memory allocation and initialization, that's those 9, and then can be easily replaced by OpenMP. So OpenMP target enter data and exit data makes it possible to put it on the device. And this example, as for the previous one, for X, we don't actually copy the data, but just allocate memory and release it at the end. And for Y, we copy it in and out of the device. Additionally, we initialize X on the device, so we use OpenMP target, and in the region we initialize X. And now we have the problem that CUDA BLAS requires the device pointer. We have currently only X, although device pointer exists. So we can use, for instance, an AP runtime routine OMP get map pointer to associate or to obtain for X the associated device pointer, which we then can feed into the CUDA BLAS library, as shown here. Of course, there are many more ways one could get the pointer in the target region, and also for memory allocations, OpenMP provides various means. For instance, unified shared memory could be used. There are also OpenMP has some means. OMP target alloc allocates data directly on the device. One could use still some CUDA or other runtime routines it then associates them with host variable for OpenMP. So OpenMP target associate pointer, which is kind of the reverse of OpenMP get map pointer. And for fancy allocations, also OpenMP allocators exist, which can be predefined or user-defined. User-defined can be pin memory, and since OpenMP 6, one has also the possibility to allocate that way memory, which is only available on a device or on the host and specific device and so on. For managed memory, there's no direct way to achieve this. GCC provides one via OpenPX new managed memory as memory space at allocator, but this runs into the same problem as CUDA calls. It's not portable, shifting the portability problem from the runtime library API to a compiler one. But still, that's one of the several ways possible. So we have now solved this way. Let's look to the next one. We need to have some association between OpenMP's default device and CUDA's current device. Actually, usually it works in a simple way as one-on-one correspondence, but if the first GPU is, for instance, an AMD one that breaks, so there's a possibility via Interop to obtain the CUDA device number and several more information. So we have an opaque object OpenMP Interop type. We call Interop init on this object to initialize it, and we say that we want to have some data available which are provided by target. So via target some are available. This gives for the specified device, and here I specified the default device, which is anyway the default, but I could specify another device. For that device, it provides some interop object from runtime, or none, if none is available, as typical for the host. I leave it by default completely to the runtime what it provides. If I have some preferences, I can tell it to the runtime whether the runtime can fulfill it or delivers me something else, including none. I cannot control it. Of course, depends also what's available, but preferred type at least gives a hint to the runtime library. Once returned, as said, if the object is not none, I can use it using some API routines, OpenMP get interop. There are 3 of them. One of them takes integers. That's the first one, and this one I use to get the front runtime identifier and check whether that's indeed the expected CUDA. If that's the case, then I continue and ask for another integer object and a string object by asking for the CUDA device number and the name of the front runtime, and running that on a default system, like for instance the laptop I'm currently running on, gives then the CUDA device number 0 and as runtime name the string CUDA. There are many others, including getting the OpenMP device number, which makes sense if I pass the interop object around. At the end, I need to destroy the object. So where do I get more information about what's available? Well, the API routines, things like front runtime identifier, device name, and whatever it means is in the OpenMP specification. But there's also, for things like CUDA driver, some documentation, namely the additional definitions document, which is part of the OpenMP specification, as shown here via the link. That shows which front runtimes are available, namely CUDA driver, OpenCL, CL, HIP, Level 0, and HSA. HSA is new in OpenMP 6. And of course, what exactly is available depends on the compiler, the libraries supported and installed, and the hardware. But a compiler should provide some information like GCC does, and GCC supports for individual GPUs CUDA driver, and HIP. and von AMD GPUs, of course, AMD SIP and also HSA. Details are in the compiler documentation, but the data types for this listed foreign runtimes is also in the additional definitions document. More to about this one in a moment. And of course, more foreign runtimes might be supported, but I think currently they aren't. Okay, now we have this one. So what one can do with it? Well, we want to use it to fix device number issue, and we don't want to do it by fixing the device number itself, but by obtaining directly a streaming object. That has advantages, as we will see on the next slide, but let's first get the streaming object. So this one looks pretty much the same as we just said. We have OpenMP Interop in it, but now instead of target, we use target sync. And target synced really calls into the runtime library to create a streaming object. So that's in a way much heavier, but one can do more with it. So we get out now the opaque object and now use the third OpenMP get interop call, this time for pointers, and ask for target sync and get out, in this case, hopefully thanks to preferred type, a CUDA streaming object, which we then can feed into the set stream of BLAS, happily run it, and at the end we destroy it. CUDA BLAS is synchronous, so everything has finished until we destroy it, but otherwise Interop destroy waits until the kernel has finished. So that we solved here. Let's have a quick look at the definition document here. That's all definitions of the data types for the foreign runtimes, just that you have an idea how this can look like. Okay. As mentioned, we want to do as much as possible concurrently on the CPU, GPU, and so on. So how to do this? Well, first we have to go to asynchronous. For target and other commands, that's no wait. But just doing work asynchronously doesn't help. We also need to make sure that we only use data available. So that's illustrated in this example. The full example with a lot of extra explanation can be found in the OpenMP examples document, because I've taken this one. In any case, this example initializes the vector x on the GPU, so OpenMP target maps then when it's finished from the GPU. As said, no wait makes this asynchronously, and we tell that it sets the x value so it depend out. On the host, we again asynchronously, which implies task, set y and have a dependency on y. Now comes the interop init for creating a streaming object. This one cannot really be asynchronous because when we start the runtime library, BLAS calls and so on, they don't know anything about dependencies, so the invert dependency is blocking on OpenMP init. So we have to depend in. But once that's fulfilled, we can go asynchronously. In order to be fully asynchronously, we need to also start the BLAS routines asynchronously, the CUDA function which permit this. So while it's still running, we then reach interop destroy, which waits until it's finished, but with no wait, we again can continue, even though it's not running, and can again set a depend out and continue, and then playing around with depend, we can continue working and continue once it is finished with task wait reward for everything. Okay. That's it for C, C++, and CUDA. Let's have a HIP example and Fortran. Interop is also supported in Fortran since some time, but to become really useful, the API routines were needed, and they are new with OpenMP 6. It pretty much looks the same. We have OMP Interop init, this time for target and target sync. And this time we prefer HIP, which in principle works also with AMD and CUDA NVIDIA devices, because HIP is written such a way, and also HIP-Fort handles it. Well, contrary to the C example, in this case for OMP get interop init, we pass not a null pointer, but an interop RC type variable, which gives a status, so we can check the status. There's also an API routine which outputs the status message in some readable message. One way it can tell that, for instance, integer is wrong and one needs to have a pointer for the question asked. Otherwise, we obtain the HIP device number, the HIP stream, and this time also a device context. For the HIP-Fort, one needs to make sure that this one is compiler specific, as all Fortran modules, so you may need to compile it yourself. So you need to get the HIP-Fort module from GitHub and compile it unless someone packages already for you. This example, by the way, is from the GCC test suite. If you use HIP with C and C++ and include HIP, well, you have to note, as mentioned, HIP, especially C version, is a very thin layer around CUDA. So the library or the header file does not really know whether you have CUDA or HIP as API calls. So you need to define the HIP platform, AMD or NVIDIA, before you do it. Well, if you have the AMD or NVIDIA compiler, the header file assumes that you have a specific one. Okay, talking about compilers. Interop itself was added to OpenMP in version 5.1. It's already quite a while ago, so one can expect that a couple of compilers already supported to some extent. 5.2 didn't change much. Version 6 added a couple of useful things you may not usually encounter, but some of them are quite useful. A bit more about those in a moment. The ones which are more useful: HSA I already mentioned, Fortran API routines as well. Attributes with preferred type I didn't show before, I will have on the last slides, and this pitch is on the next slides. Compiler support, GCC 15 added most of it, including version 6. It just asks, missed the deadline with the changing, but if you don't use variadic function, you unlikely need to know about those features. And GC 15 should be enough. The Intel compiler has support for it, and HPE CCE compiler also has, and probably some others have as well. For HPEs, I saw also Fortran API routines in some examples, so they seem to have this 6 feature as well. And for Intel, I quickly show this example because Intel supports SYCL, which most of us don't, and for preferred type, this shows that one can also use numeric value, so these predefined constants instead of using a string as I had before. Otherwise, it works the same way. So to summarize, one can have with OpenMP nice management memory and reduce the vendor specific code, but Interop permits much more for asynchronous tasks. The dependency handling is quite useful. Okay, that's it on this part. I want to continue with declare variant, because then we can abstract the library calls very much and make it locally much nicer and have the heavy lifting or the specific parts in one common place. Well, variant function, if you don't know it, they permit to have to declare a variant function to a base function. The base function or is the function one usually has, and the variant is supposed to be called under certain conditions. It of course needs to have the same function prototype, and otherwise one just defines it, and then immediately before the base function one puts the OpenMP declare variant, puts the name of the variant function. There can be multiple variants, and then a condition, and OpenMP calls this context selector. The example I use here is a global variable as condition, and if you look at the example in the bottom, base function calls the base function because the global variable is false. If I set it to true, have the same call, then under the hood the variant function is called. There can be many more context selectors. For instance, if it's directly in a parallel construct in a structured block, then construct parallel is a match, or if I have target device where the default device number matches then the kind GPU, then this one is used, but I can also ask for certain compiler vendors, or for the GPU, certain GPU types or things like that, and combine many of those. Okay, that's what we want to use for going to the device. So if we now look at vendor call, again, I stay with the kublas DAXP, which I want to call, and then I want to call a C function wrapper around the Fortran function, which is also DAXP, and essentially looks the same, but it's not quite the same. There are two differences. For the kublas function, of course, the obvious difference is that it takes a handle, but additionally the function also wants to have for the vectors a device pointer, or at least we want to put a device pointer. So how do we handle it? Well, we of course write a wrapper for the kublas function and then create a variant that looks like that. So we have a device DAXP, a declare variant. We assume some match function, and one can think about what is sensible there. And in the function, of course, we have to handle the missing bits. So we create a stream and later destroy it. And we also need to convert the host pointer to a device pointer. And the used device pointer assumes that before the call was done, the data is actually already on the device. So we just need to find the associated device pointer and not actually copying data. That's pretty nice, but of course we would like to get a bit rid of the used device pointer in the call here and move it into the callee. That's what we want to do now. As said, the used device pointer is hard-coded and we have some context to fulfill. Well, now let's use as context OpenMP dispatch and remove the target data from the device DAXP function and use the new feature to declare variant adjust args. There we say that we need a device pointer for dxdy. So in the variant call, it essentially does the same as the crossed out line. It goes to the device pointer. In order to avoid surprises, so that it happens somewhere randomly if one calls the DAXP function, it was decided that adjust args only works with construct dispatch. You can have more context selector, but dispatch is always required. But this has also some other advantages you will see next page. Not only that it alerts the user that something might happen with a device call, but it also permits more. That's I have here. Besides the normal OpenMP dispatch, which just calls it and converts it to a device pointer, I can also tell that it is already a device pointer and there's no need to convert. That's something I couldn't do with the putting it into the call. There's also a nice feature which is called no context. Context construct dispatch is inside the dispatch is a context, and if I say no context, then it doesn't care about this context and other context, and that can be used as in this example. If n is a small number, I calculate on the host. If it's large, I take the overhead of stream creation and so on and call it on the device. There are some other features, especially for Fortran, but also for C++. One can has the device address, need device address, and has device address. That's in OpenMP 6 features. Multi-compilers already have it, and as said, for Fortran, it's quite useful. And there's also no variant, which disables all variant replacement, which can be useful also without these adjust args things. Depend and no wait are also possible, which can be quite useful. Okay, now we have replaced the device part. So what can we do about Interop? So as mentioned, it's currently hard-coded. The streaming object, of course, we can instead of the streaming object use an Interop object that only solves it half away. Of course, there's now the better association with OpenMP in terms of the default device pointer, and we get the Interop object, but you still have it inside the function. As you might have guessed, we add now something to declare variant to get a streaming object. Namely, we have append args. There we take an interop object, and this one now takes a streaming object, so target sync. And as append args implies, after every normal argument, at the end we put the interop object. So we can use it in the device duxp function. And besides all the advantages of having it automatically, we have other advantages. For instance, if I now change the device in the dispatch, then automatically a streaming object is created for that device. Otherwise, inside the function, I would have to do something. And since OpenMP 6, I can also pass an interop object directly if I have it for some other reasons already ready. Well, that's on the streaming object side. And that's it for this talk. As a summary, one can use interop and declare variant to make the life much easier, including handling dependencies and OpenMP and GPU vendor runtime library support, of course. Features like declare variant might be useful for other things, and interop can be, as seen, also used in some other cases. On this last page, I also want to show quick some variant of preferred type. The first preferred type is as known. The second one for the other function uses a new syntax, which doesn't really buy much, but is also supported. But this new feature, new syntax permits for new features. That's the last line, where I say I want to have the front runtime circle, but I want to provide some additional argument. OpenPX means it's vendor specific. I now simply wrote OpenPX in order. I have no idea whether any vendor supports this syntax, but for circle it's particularly useful because the queue can be in order or out of order. Out of order is default, but with in order one can avoid barriers, so it's pretty useful. I don't know whether Intel supports it, but if not yet, maybe in the future. Otherwise, several compilers support it, I guess. The new syntax, GCC does, but currently I didn't find a use for it, so it just ignores it. And preferred type is anyway a hint. Okay, that's it from my side. If you want to see more OpenMP tech talks, you can find them at the link below. There you also find the slides of this talk and the recorded video. Otherwise, OpenMP.org has much more other information as well. Thank you for listening.